In this video, we're going to talk about limit points and also a special type of topological space which is called Hausdorff space. Okay, let's start with a limit point. So let me first give formal definition of limit point, and then I'll give you some example. Okay, let's say X is a topological space. X is a topological space, and A is a subset of X, and also let's say this lowercase x is an element in a topological space X. Okay, so we have like this. Let's say this is our topological space X, and we have a set A here, which is a subset of X, and then we have a point X. This point X, it could be inside A or outside of A. Let's say we have here this X is an element in the topological space. This X, which is an element of in the topological space X, it could be outside of the subset A or inside of the subset A. It doesn't matter. Okay, then this X, which is an element of X, is a limit point. Which is also called cluster point, a limit point, cluster point, or which is also called the point of accumulation. Then this guy X is a limit point or cluster point or point of accumulation of the subset A if every neighborhood of this point X, if every neighborhood of the point X intersects A in some points, other than X itself. So this point X is called the limit point of the set A if every neighborhood, so here it says the every neighborhood of X, neighborhood means an open set containing the point X, which is called the neighborhood of X, which you have learned in our previous video. So if every neighborhood of X, that means if every open set containing X intersect this set A in some point other than X. So if X is inside A, then that, let's say this is the open set U, which is an arbitrary open set U containing the point X. That means U is an arbitrary neighborhood of X. If this neighborhood U of X intersect the set A other than x. So in this case, if x is outside of a, then this u intersect at some point of a. And let's say if x is inside of a, then every neighborhood of u, or the arbitrary neighborhood u of x, should intersect a at some point other than x. Then the point x is called limit point, and which is also called, that is if u is an arbitrary, since it says the every neighborhood, that's why that is if u is an arbitrary, if u is an arbitrary neighborhood, that means is a neighborhood of x. If u is an arbitrary neighborhood of x, then u should intersect at some point, you should intersect a at some point other than x. That means if we remove x from a, and then if we take the intersection of this guy with u, the intersection, it must be non-empty. Then the point x is called the limit point. So basically, the x is a topological space, and a is a subset of x. Then a point x, which is obviously in the topological space x, this point x, it could be inside a or outside of a. Then this point x is called limit point of this set a. If every neighborhood of x intersect a at some point other than x, that means every neighborhood. So if you take the intersection of every neighborhood of x with a minus x, that intersection must be non-empty. Then the point x is called the limit point. Okay. All right, now let me give you okay, so then the set of all limit point of the set A, which is denoted by A prime, the set of all the limit points of A is denoted by A prime. Okay, A prime, that's the notation for the set of all limit point of the set A. And that means A prime, it could be the set of the element inside A or outside A, because the limit point, it could be inside A or outside of A. Now let me give you example. Here is our first example number 1. Let's say X is a topological space whose elements are A, B, C, D, and E with the topology. Let's say X is a topological space with the topology tau. It's obviously empty set is in the topology, and the whole set X is in the topology, and this 1-point set A, 2-point set CD, 3-point set A, C, D, and 4-point set B, C, D, and E. Okay, so we are considering this topological space with this topology. Now let's see which point of X are limit point of this set A, B, C. This is obviously a subset of X. Now we're going to figure out which point of X they are limit point of this set A, which is the subset of X, and which are not. Okay, now let's start investigating with B. Now here we're going to use that definition. Okay, so now here we are trying to figure out whether B is a limit point of the set A or not. By the definition, this B is said it's called the limit point of A if every neighborhood of B, neighborhood of B means the set the open set containing B. Open set means here the open set in our example open set, these are our open set, or the elements of topology, these are the open set. So every open set containing B should intersect A at either at A or at C. Okay, now let's see the neighborhood of B, which are obviously X itself is a neighborhood because X is an open set containing B, and then the other neighborhood is this one. This is the open set containing B. So there are only two neighborhood of B, and let's say whether those neighborhood intersect at A other than B and the point B or not. And if you take the intersection of X with A, this set A, then the intersection is gonna be A and C. So that means this neighborhood intersect A at some other point than B. So that's fine, and the other neighborhood is this one. So if you take the intersection of this set with A, our intersection is C. So that means intersection is B and BC. That means this neighborhood also intersect A other than the point B. So that means the point B is a neighborhood of A. Now in this case, our limit point is inside A. Okay, so just let me write down the thing that I just described here. B is a limit point. This is a limit point since the neighborhoods of B are the whole set X. Let me go to the next slide page, and which is B, C, D, and E. The neighborhoods of B are the whole set X and this set, and each neighborhood and each contains points of A other than B, so that B is a limit point. So here we found that B is a limit point. Now let's see whether the first guy A is a limit point or not. So the neighborhood of A, which are the X, obviously X intersect A at B and C, so that's fine. And the other neighborhood is this singleton set A of A. So we are investigating whether this lowercase a is a limit point or not. Since this is a neighborhood, this singleton set is a neighborhood of A, and if you take the intersection of this neighborhood with the set A, then the intersection is simply the point A. So it does not intersect the set A other than the point A. So we cannot say A is a limit point, because every neighborhood of A should intersect the set A at some point other than A. But this neighborhood does not intersect the set A other than A. So we cannot say A is a limit point. So here, let me just write down that things here. A is not a limit point. A is not a limit point. A is not a limit point of A, because A is not a limit point of A because the singleton set A is a neighborhood of A and intersects A, the set A, only at the point or the element A itself. Okay, So far we found that A is not a limit point and B is limit point. If you do the similar investigation, you can see that you can see that D and E, they are going to be a limit point, but not C. You can check that one. Okay. Similarly, the points D and E are limit points. You can do the similar investigation. Limit points, but C is not. Okay. So finally, we found all the limit point of the set A, which are A, D, and E. So thus A prime, this is the notation for the set of all limit point of the set A, and in our example A prime is B, D, and E. So this is the set of all limit points of A, and you can see here our set is ABC, but the limit set of limit points of A, which is B, D, and E. So we can here A is not the subset of A prime, and also A prime is not the subset of A. That means some of the limit point of A which are outside of A. So if you are finding the limit point of the set, then it's not mandatory that those limit points should be inside the set A. Okay, now let me give you another example. Example number 2. Now let's take our topological space is the set of real number with standard topology. Okay, with the standard or order topology. So here, since we are taking standard topology or order topology in R, so the basis element or the open set in R, which are the open interval of this form. Okay, you guys have seen this before. All right. In the part A of this example, let's say our set A is this half open interval with 0 is included and 0 is not included and 1 is included. Obviously, this half open interval is a subset of R. Now we're going to investigate, or we're going to determine the limit points of the set A. So we have 0 here and then 1 here. So this is our real line. This is positive infinity side. This one is negative infinity side. Okay, now let's start with investigating the point 0. Since we are taking the standard topology on R, so the open set in R, these are like those open intervals. Okay, and so let's see whether 0 is a limit point of this set or not. If 0 is a limit point, then every neighborhood of 0 should intersect the set A at some point other than 0. So neighborhood, like I said earlier, neighborhood of 0, which is an open interval containing 0. So if you take the open interval containing 0, then the sum part is gonna be on the left side of 0 and the sum part is gonna be on the right side of 0. So this is the, you can say this type of the interval, they are going to be a neighborhood of 0. So no matter which neighborhood you pick here, since some portion of that neighborhood it goes to the left side of 0 and some portion it goes to the right side, and then you can see that right side portion, that's gonna be the intersection or non-empty intersection of A minus 0 with that interval. So no matter which neighborhood of 0 you take, that will intersect at some other point then 0. So we can say that 0 is a limit point of A. So here we found that 0 is a limit point of A. Then just let me write down 0 is a limit point. 0 is a limit point of A, because every neighborhood of 0 that's gonna be on both sides, left and right side of 0, and that right side portion is the that will intersect at A other than 0. And also now here we want to find all the limit points. So so far we found 0 is the limit point of A, and let's see the midpoint of that center. Let's say the midpoint is 1/2. Then the neighborhood of 1/2 is obviously is an open interval like this one, and the open interval containing 0 that goes both sides of left side and the right side of 1/2, and no matter it goes left side or right side, that will obviously intersect A at some other point than 1/2. So 1/2 is also a limit point, and so then 0 is a limit point of A, and also 1/2 is a limit point. Is a limit point. So you can see here, in fact, if you pick any point if you pick any point on this set A, then you can see that that point is going to be a limit point. Okay, so no matter which point you pick from that interval, from this half of an interval, the neighborhood of that point will intersect the set A at some point other than that point. So every point of this interval, half open interval, is going to be a limit point, and we already know that 0 is a limit point. Okay, so in fact every point of 0, 1, this half open interval, in fact, is let's say the closed interval is a limit point. Okay, so we found that every point of this closed interval 0 to 1 is a limit point. Now let's investigate the point outside of that closed interval. Is going to be a limit point or not? Something like this here. Let's say this point. Now here, this point is going to be a limit point of A if every neighborhood of this point, let's say, is -1. Every neighborhood of -1 intersect A at some point other than -1. Now here we can easily find a neighborhood, this neighborhood of -1, which does not intersect A at all. Okay, so that means -1 is not the limit point, and so here you can similarly investigate the other points outside of the closed interval 0, 1. You will find that those points are not going to be a limit point of our set A. So in fact, every point of this closed interval is a limit point. But no other points of R, that means other real numbers, between other real numbers, is limit point. So our A prime is simply this closed interval 0 to 1. So these are the any real number between 0 and 1, including 0 and 1, is the limit point of this set A. Let me give you another example. Still we are in the real number with the standard topology. Now let's say in this case our set is the set of all reciprocal of let's say the natural number. Okay, so here our set is basically, this is our real number, real line, negative, positive infinity, negative infinity, and we have 0, and this is 1. So our our subset B is the set of reciprocal of natural number. That means if we take the reciprocal of 1 is gonna be 1, and if you take the reciprocal of 2 is going to be 1/2, and if you take the reciprocal of 3, that's gonna be 1/3, and then you keep going close, and you're going to be very close to 0. Okay, now here it is easy to check that 0 is a limit point of B, because if you take any neighborhood of 0, that will go to the both left side and right side of 0, and then the right side portion is it will intersect B at some other point than the 0. So 0 is a limit point, but 0 is not not an element of the set B. So it is easy to check that B is a limit point. Now let's check the remaining point. Okay, so here 1 is an element of B, but 1 is not going to be a limit point of B, because we can create a neighborhood of 1, or the open interval containing 1, which intersect the set B at only one point, which is 1. So 1 is not a limit point of B. And similarly, you can check every point of B is not going to be a limit point of B. So only the limit point is 0, because we can, for example, we can to check 1/2, you can construct an open interval containing 1/2, which will intersect B at only 1.1/2. And the outside of B, for example, if you pick the point -1 here, we can find the neighborhood of -1, which will not intersect B at all. So -1 is not the limit point of B. So if we take any real number other than 0, then you can see from here that neighborhood will either intersect the B at that point only, or will not intersect at all. So only the limit point of B is 0. Okay, just let me write down the thing that I just described here. Then 0 is the only limit. 0 is only limit point of B, and every other point X in R, or every other real number other than 0, every other point X in R has a neighborhood. It's a neighborhood that either intersects B at X X only, or intersects B not at all. So the point 0 is the limit point of B, which we can see from here, and every other point X in R has a neighborhood that either intersect B at X only, or intersect B not at all. So B prime is only a 0. Okay, now let me give you one more example. Still we are in the set of real number whose subset is this union of the singleton set 0 and this open interval. So here this is our 0 and this is the open interval. We have 1 to 2. And here it is easy to check that 0 is not going to be a limit point, because we can construct a neighborhood containing 0, which will intersect the 0 only. On this interval from 1 to 2, 1 is going to be a limit point, because the open set or neighborhood containing 1, that will go to the both left side and right side of 1, and the portion on the right side, that's gonna be the intersection with C. And also by the similar reason, we can say that 2 is also a limit point, because the portion on the left side of 2, that's gonna be that is going to be the intersection portion, and also any point between 1 and 2, that's gonna be the limit point, but no other points that's going to be a limit point of C. So here the limit points of C are the points of the interval of this closed interval 1 to 2. Okay, and so C prime is simply this closed interval. One more example. Let's say our subset is the set of rational number. Is the set of rational number. Then the set of rational numbers. So in this case, the limit point of Q, that going to be set of all real number, because any interval containing a real number that contains both rational and irrational number. Let me repeat one more time. So if you have a real number, it doesn't matter it is a rational number or irrational number. Let's say that is my rational number, and the open interval containing this rational number, it contains the point, it contains the rational and irrational number both. Since this open interval of R, no matter which open interval you take, it will have both rational and irrational number. That means that interval will intersect B at some point other than R. So that means this rational number is a limit point of Q. And also, instead of this rational number, if you take the irrational number, R is a irrational number, like I said earlier. So if you take an open interval of real number containing a real number, that open interval will contain both rational and irrational number. So no matter R is real, rational or irrational number, this open interval, and no matter what open interval you take, that open interval will contain both rational and irrational number, and that rational numbers, the set of rational number, that's going to be that's going to be the point of intersection of this open interval with Q, except with the set of rational number Q other than R. So here we can say that the limit point, set of limit points of Q is the entire real number. Okay, then every point of R is a limit point, of Q. Again, Q is the set of rational number here. So Q prime is R. Okay, now here one more example. Okay, let's say our subset of real number is G plus, which is the set of positive integer only. Okay, so here this is our real line, this side is positive infinity, this is negative infinity. So our set is 1, 2, 3, 4. We are taking only the positive number. And now you can see for each positive number, or sorry, each positive integer here, we can construct the open interval that will intersect the set only at that positive integer. For example, we can have the open interval containing 1, like this one, which will intersect this set at 1 only. And also for 2, we can construct the similar open interval containing 2 that will intersect this set at 2 only. Okay, and similarly for 3, similarly for 4. That means none of those points, they are going to be they are going to be limit points. So in fact, for g plus, or for the set of positive integer, there is no limit point. So then no points of R is a limit point of g plus. Okay, so we can say that g plus prime is a empty set. So these are the some example of a limit point. Okay, all right, now next I'm going to give a theorem which gives us a relation between a set and its closure, and also the set of limit point. So I'm gonna give you a theorem without proof, and here is the statement of this theorem. Like I said, this theorem will give us the relation between a set, its closure, and the set of its limit point. Okay, let's say X is a topological space, and A is a subset of our topological space X, and A prime is a closure of A. Sorry, A bar is a closure, not prime. A bar is a closure of A, and A prime is a set of all limit points of A. Then this A closure is going to be the union of A and A prime. Basically, if you take the union of given set with the set of its limit point, that union is going to be same as its closure. So this theorem it gives us the relation between the given set, its closure, and the set of its limit point. So like I said, I'm not going to give the proof of this theorem, and if you are interested in proof, you can take a look in Munker's book. Now we're going to use this theorem to find the relation between between a closed set and its limit point. Okay, and which is you have as a corollary. So this corollary, it gives us the relation between a closed set and its limit point. Again, we are our topological space is X. A subset of a topological space, is closed if and only if it contains all its limit point. So you can see here this corollary gives us the relation between a closed subset of topological space with its limit point. If your subset is closed, then it contains all its limit point. That means A prime is going to be subset of A, and if a set contains all its limit point, then that set is going to be a closed set. You can see this is if and only if statement. So we have both side implication. That means if the set is closed, then it contains all its limit point, and if the set contains all its limit point, then it's gonna be closed. Okay, let's prove this corollary. Let's prove this this side first. That means if A is closed, then we should show that it contains all its limit point. Suppose X is not X. Suppose A is a closed subset of X, then by definition of closed set we can say that A closure is A, and here we want to show that A contains all its limit point. That means we want to show that A prime is a subset of A. Now we're going to use our theorem, this theorem here. So this theorem, it tells us A closure is same as the A union with A prime. Then so by above theorem we can say that A union A prime is A closure. But since A is a closed subset of X, and A closure is gonna be the same as A. Now here we found that A union A prime is same as A. That means, so this implies that this A prime, it has to be a subset of A. If A prime is not the subset of A, then we cannot say that union is same as A. So this implies that A prime is a subset of A. Since A contains A prime is a subset of A, which means A contains all its limit points. So that is what we wanted to prove here. So this side is done, and the other side, let's say let's assume that A contains all its limit point. Then we need to show that A is closed. Suppose A contains all its limit point, okay, A contains all its limit point, then we can say that A prime is a subset of A. If it contains all its limit point, then A prime is a subset of A. So again, by the above theorem, we have A closure is A union A prime, but A prime is a subset of A. That's what we have here. If A prime is subset of A, then if you take their union, then that's gonna be A. Now here we just prove that A closure or A bar is same as A. So that implies that A is closed. Okay. So that will prove this corollary. All right, now this corollary is very helpful to check whether the given subset is closed or not, and or whether the given subset of a topological space contains its limit point or not. Okay. All right, now the next we're going to discuss a special type of the topological space, which is called the Hausdorff space. Okay, Hausdorff space. So let me give you a definition of Hausdorff space, and then I'll give you some examples. So as I said before, this is a special type of topological space. Let's say X is a topological space. We have this topological space X. Let's say X is a topological space. Then let me just write down the definition first, then I will describe the definition. Then X is called a Hausdorff space called a Hausdorff space. It's called Hausdorff space if for each pair of for each pair x1 and x2 of disjoint, it's called Hausdorff space if for each pair x1 and x2 of disjoint points of x. So for each disjoint point, like this one, disjoint means they are a distinct point. For each pair of distinct point in x, there exists neighborhood u1 and u2 of x1 and x2 respectively that are disjoint. Okay, this is the formal definition of Hausdorff space. A topological space X is called the Hausdorff space if for every pair of distinct point like x1 and x2, these are the distinct point. For every pair of distinct point, there exists the disjoint neighborhood like this. Let's say this is u1 and this u2 is the neighborhood of x2 and which are disjoint, right? So if this property holds for every pair of distinct point in the topological space, or that means for every pair of distinct point in the topological space, if we can find two disjoint neighborhood u1 for x1 and u2 for x2, then that topological space is called Hausdorff space. Disjoint means if you take the intersection of u1 and u2, the intersection must be empty set. Now let me give you a couple of examples here. Example number one, let's say a topological space X with a discrete topology. A topological space X with the discrete topology. Remember, discrete topology means that is basically the power set of a given set. So where all the singletons are open set. Okay, a topological space X with discrete topology tau is Hausdorff. Okay, for example, let's say if X is a topological space and whose elements are like this, and so if you are taking the discrete topology tau, then it's the power set of this set, and in power set obviously you have those singleton. These are like the open set. That means each singleton is going to be a neighborhood of that point. For example, let's say if this is x1 and this one is x2, if we are taking these two distinct elements of x, then in order to be this guy Hausdorff, we need the disjoint neighborhood of x1 and x2. So like I said, for this x1 we can take this singleton as a neighborhood of x1 because singleton is open set in discrete topology, and for x2 you can take this singleton as a neighborhood of x2. Since x1 and x2 these are the distinct, and those singleton they have just one point, so obviously those singleton those neighborhood of x1 and x2 they are also disjoint. So if you take a topological space with a discrete topology, then that topological space is going to be Hausdorff space. So you can see that the Hausdorff property, it depends on the topology. So this is an example of Hausdorff space. In example number 2, let's say X is the set of real number with standard topology, standard or order topology, standard or order topology. Then X is its Hausdorff. So it is easy to check this one. Let's say this is our real line, this side is positive infinity, this side is negative infinity. If it is Hausdorff space, if you pick any two distinct real number, let's call them x1 and x2. These are two distinct real number with x1 is smaller than x2. Okay, since x1 and x2 are the distinct, so in real number, if you have two distinct number, you can compare them. Let's call that x1 is less than x2, and in order to be this real number, set of real number is a Hausdorff space, we should be able to find the neighborhood of x1 and neighborhood of x2, which are disjoint. And since we are taking the standard topology, neighborhood of x1, or in the standard topology or order topology, the open sets are like the open interval. So here we should be able to find the open interval of x1 and open interval of x2, which are disjoint. Okay, now something like this. Okay, this one. So this one is going to be the open interval of x1, and that is going to be the open interval of x2, and they are disjoint. Now here, if you want to find what is exactly that point and what is exactly this point, what you can do here is you can take this distance. You can take this distance from here to here. That is going to be x2 minus x1, and you divide by 2. If you from here to here, that's from here to here is x2 minus x1, and if you divide by 2, then that is going to be the center of x1 and x2, and this is the center. And you take this part from here to here, and also you go to the left by same distance of x1. That is going to be the neighborhood of x1, and also for the neighborhood of x2, from x2 you go by this distance, which is x2 minus x1 over 2. So that's the midpoint. And also you go to the other side by x2 minus x1 over 2. So that will be the neighborhood of x2, and we can take this one is u1 and the other one is u2, and u1 and u2 they are going to be disjoint. So here if you take like this one, then so this point is gonna be x1 plus x2 minus x1 over 2, x2 minus x1 over 2, and this point is going to be x1 minus x2 minus x1 over 2. Just you subtract this distance from x1, that will give you this one. So it's gonna be so the open set or neighborhood of x1 is going to be x1 minus x2 minus x1 over 2, comma x1 plus x2 minus x1 over 2. This is the neighborhood of x1, and then you take the intersection with the neighborhood of x2. Neighborhood of x2 is gonna be x2 minus x1 over 2, comma x2 plus x2 minus x1 over 2. So that is the neighborhood of x2, and this neighborhood of x1 and this neighborhood of x2. From this figure you can see these are disjoint. So we are able to find two neighborhood of distinct point x1 and x2 which are disjoint. Since x1 and x2 are two arbitrary point, so that this property is true for any pair of distinct point in R. So we can say that R is Hausdorff space under the standard topology. One more example number 3. So this time I'm going to give you example of a topological space which is not Hausdorff. Okay. All right. Let's say X is a set of real number with finite complement topology. So we have already seen that R with the standard topology is a Hausdorff space, but the set of real number with finite complement topology is not Hausdorff. So here, what is the finite complement topology? Finite complement topology, which we denoted by tau f. You have seen the definition of finite complement topology in the very first section, which was the topological spaces. You can go back to the that video and you can take a look. You can watch that video. You will see the definition of finite complement topology. So finite complement topology is the set of those subset of R such that if you take the difference of that set or that subset U of R, then that difference, it has to be either finite or it has to be all of R. So the collection of those subset whose complement is either finite or all of R, then that collection is called finite complement topology on R. And we are saying that this the set of real number under this topology is not Hausdorff, and we have already seen that the set of real number under the standard topology is Hausdorff. Now you can see that the Hausdorff property, it depends on the topology. Okay, now here now you can see why the set of real number is not Hausdorff with the topology with the finite complement topology. Let's say we're going to use contradiction method. Contradiction method means, let's say this set or this R is a Hausdorff space with finite complement topology. Okay, so I'm going to give a brief proof of this one. Proof. Suppose R is Hausdorff. R is Hausdorff under the finite complement topology. Okay, so if it is R is Hausdorff, then for any two real number, so Hausdorff, then Hausdorff, and suppose that x1 and x2 are two different real number, then there exists u1 and u2, then there exists u1 and u2 it's a neighborhood of x1 and x2 respectively. There exists the neighborhood u1 and u2 of x1 and x2 such that u1 intersection u2, it has to be complement. Okay, if u1 intersection u2 is complement, which implies that u1, it has to be inside the complement of u2. So this C means complement. So basically what you have here, we have the situation like this. This is real line. We are taking x1 here and x2 here, and this is the open set we have here, or this is our u1, and we are taking u1, and this is u2. It's the open set or neighborhood of x2, and these two are complete. These are two are disjoint. I mean, they don't intersect here, and if they don't intersect here, then you can see here this u1 is inside the complement. Complement of u2 is the this part, right? Everything but u2. So obviously u1 is inside the complement of u2, and u2 complement, which is basically, you can say that R minus u2. Since u2 is the open set, if u2 is the open set, then by definition of finite complement topology, if u2 is in tau f, that means if u2 is open set, then is in the topology. If u2 is in topology, then the complement of u2, it has to be finite. Okay, it has to be finite, or R. It cannot be the whole thing R, so it has to be finite. So that means this complement is finite. So u1 is the subset of finite set. If u1 is the subset of finite set, then u1, it has to be finite. Okay, all right. Now we can write down R is the union of u1 complement and then also u1. If you take the given set and its complement, then you're gonna get the whole set. So in our case, the whole set is R. So if you take the union of u1 with its complement, then you're gonna get the R. And here we just found that u1 is finite. And since u1 is the neighborhood of x1, that means u1 is an open set in finite complement topology. If u1 is open set in finite complement topology, its complement R minus u1, it has to be finite as well. Now here you see that R, we are writing R is the union of two finite sets. So that implies that R is finite, and that is not possible. We cannot say R is a finite set. So which is a contradiction. That means our R is not a Hausdorff space with a finite complement topology. Okay, all right. So this is an example of a topological space which is not Hausdorff space. Okay, now I'm going to give a statement without proof, and that statement will give the relation of Hausdorff space and its closed subset. So just the statement, and if you are interested in the proof, you can take a look in Munker's book. And this theorem, it tells us that every finite point set in a Hausdorff space is closed. Okay, so if you take a finite subset of a Hausdorff space, then that subset is going to be closed. So this theorem is very useful to check whether the given subset is in a Hausdorff space is closed or not. So if you take the finite subset of a Hausdorff space, then that set is going to be closed. Okay. Again, I'm not going to give the proof of this statement, but if you are interested in proof, you can take a look in Munker's book.